All right. Excellent. So, looking at chapter 14, this is when we're going to kind of wrap up the definitions that we're going to need to start really doing calculus. Now, we've done some calculus on space curves, which were what? Vector functions of a single variable, right? That had a single independent variable where we could parameterize that curve through space. What we're going to be looking at today is actual multivariable functions, meaning, right, because like parametric functions or vector functions were kind of tricky in that they had multiple variables, but those were all dependent on one independent variable, right? So here we're going to be looking at things that have more than one independent variable. So we're going to look at how we define that, look at it from the multiple perspectives like we typically do here at this school, which I love, which is looking at graphs, tables, the algebra, and the verbal definitions, all four of those things, is kind of like outlining our perspective on functions. We'll look at some graphs, but we'll look at an even more useful tool, which is called level curves or level surfaces. And these things scale up well to n-dimensional spaces. And then we'll look at the ideas pretty briefly of limits and continuity. These would probably get a more formal treatment elsewhere. And we're going to look at why it's a bit more complicated now that we're in 3D, and some ways that are easy to show that a limit doesn't exist. And I'll point to why it's a little tougher now to show how a limit does exist. And then continuity carries the same connotations as it did before. So not too terribly much new, but again, kind of broadening that perspective overall. So starting off with functions. Oh, pencil's dying on me. Something's happening. Okay, let me reboot this real quick. Okay, that works. Okay, rewind. We'll try that again. What was I saying? Here we go. So multivariable functions. We're going to start off looking at functions that have a real output for multiple real number inputs. Okay, so here's some examples of what I'm talking about and why this is going to be different from, if you recall, y equals f of x. This is a single valued function or single variable function. It takes an input x and maps it to y. And we can visualize it on the graph by looking at the pair xf or xy. Hopefully that's not coming as news to you at this point, but helpful to see a parallel. So some examples of multivariable functions. So what you could think of is a temperature function, okay, which tells us maybe it'll give us something like this, e to the xy. And what this does is gives the temperature at coordinates x, y. Okay, so you input like a latitude and longitude. and this is obviously not the actual a model for temperature. This is just a random formula here, but we see in the formula itself, I have space for two inputs, x and y. What I enter there will give me a single output for temperature. And why I use this function, this is actually really good to visualize a 3D function, one that has two inputs and one output in the 3 space. Because you can think about like being on the plane, the xy plane, and then the temperature being the height of the surface that you're on. Okay, so kind of measuring the heat over point xy, it's like the height of the thermometer, right? The mercury in the thermometer. There is a function from evolutionary biology which is simple and nice and easy enough to explain in 30 seconds in this course. This measures the change in a trait. This measures kind of the heritability. So how closely related are organisms to each other on a DNA basis or on a trait expression basis? That's what this like H is. That's an estimation. And then S is what's called the selection differential. And what this means is it's negative if you see most beings in the population that don't have this trait, or it's positive if you see most beings in the population that do have this trait. So you're kind of getting a measure of how a trait is changing, that delta Z, over time. And what does it need? It needs these two variables, right? H, which you'd gather from just data collection on a population, and then S, same thing. And these two things, right, very independent of each other. So it depends on two independent variables, and we get this output. And this is what's called the Breeder's equation. And it's a very simple equation, but it's said to do a very nice job of what it does. A couple more examples of multivariable functions. So you might recall this from, pre-calculus, the exponential growth function. And, we gave it to you such that the initial deposit and the rate of growth, these were parameters, and this was a function of time, a single function of time. But really, all those things vary independent of each other, right? So really, this whole thing is a multivariate function, which we could call Q of P, R, and T. Because turning the dial on any one of these values changes how much is in the account, right? So really, it's a 3-valued input, 1-value output. So, and like pretty much every function we gave you up to pre-calc was like that, right? It's really multivariate, unless we really simplified the situation. And those parameters can vary independent. So the reason that we care about that is because reality is multivariate, right? Reality is not just shooting the grapefruit up in the air and seeing how fast it goes, right? How far it's going to fly. It's multivariate. There's a ton of things going on, and we want to be able to measure the change with respect to each of those different things that are changing that we care about, right? Each of those different dimensions. So, how is the change in this account affected by playing with nudging around the initial investment? How much is it changed by playing around with the rate? How much is it changed if we move forward or backward in time? And so you can kind of use that to generalize out about anything that has multiple dimensions to it. This is the idea of partial derivatives, which we'll be getting into next time, measuring the change of a quantity with respect to only one of its independent variables. Because now it's not just time, right? It's changing each of these things, and you need to play with those dials separately. So there's all sorts of things. There's, you could think of like a cost equation. So I was thinking recently, like at the college, we have costs that are administrative and faculty, right? So it depends on the admin costs, faculty costs, and let's say also time. Let's say things are inflating over time, right? Exponentially. So you might have some initial costs and the rate associated with the faculty cost of living going up, right? Our salaries and the prices for resources we need for teaching and whatnot. You have the admin doing the same thing. Their cost of living goes up, their salaries get negotiated, et cetera, et cetera. Those are costs that are being added, right? And here again, we have the total cost is based on all three of these variables that are independent. And you can talk about the total cost at the college in a more dialed in way, right? If we just thought about costs, period, without thinking about the different contributions, we couldn't have a helpful analysis, right? If we see that one group has higher costs than the other, then that's, well, can we come up with an explanation for that? Oh, probably can, right? But things like this, you can distribute the analysis within the variables. All right, this is probably too many examples, but I like to hopefully find a doorway in. So we'll get to measuring that rate of change later. And let's take a look at just playing with one of these things in a simple way. So let's say I've got given some function g of x, y, and it's a conglomeration of things cosine xy minus ln x over y. Say find g of 1, 3. Well, this is really as simple as, right, replacing 1 wherever you see x and 3 wherever you see y. Let's get 1 squared cos of 3 minus ln of 1 over 3, which is really ln of 1 minus ln of 3. ln of 1 is 0, if you recall, so this is really just cos 3 minus ln 3, which we could get some scalar value, right? It outputs a real number. So we can do this. Let me do it like this. Right, we can do this with any pair. So here's, 1, 3 out here, and it draws it up to some point z. So here's g of x, y, or here's g of 1, 3, let's say. So again, you can kind of think of the height over the point as being like the temperature at that point. So why don't you go ahead and find g of negative 2, 5. Any problems?
Shouldn't that be -10 if that's -2 times 5?
Yes. I was trying to come up with a witty joke there, but I got nothing. I just made a mistake. So, yes, that should be -10. I don't know why I thought, oh, because the 4. But yes, that is a problem. Other problems. There's one more that's lurking. That wasn't the one I was thinking of.
The negative natural log.
Yeah, this is not in the domain of natural log, right? So this here doesn't exist. So we're going to talk about domain and how we consider that with two variables now. But if we, switch this up and said, all right, instead of at -2, 5, that's clearly not in the domain. At 2, 5, then we can fix that problem. This becomes 4 cos 10 minus ln of 2/5. This is surely in the domain, right? And so let's say it's not going to be huge, 4-ish. So it'd be around here, let's say. So at 2, 5, somewhere out here, got this g of 2, 5. And again, you can think of the height of that point as being like the temperature over 2, 5, or the temperature at the coordinates. So that's going to be, it's going to have a gradient to it, right? And it's going to be a surface as we move around the xy plane. The temperatures are going to vary based on these formulas. Okay, so based on whatever rule this is, that's going to dictate what the height of the thermometers are, so to speak, over the whole xy plane. That's a helpful visualization tool, especially when we up it a dimension. So that's why I use that there. It might be not too hard to visualize right now, but it will help when we go up one more dimension. So just simply playing with the algebra, that's nice. Now I'd like to take a look at from the numerical perspective, looking at a table and analyzing multivariable functions. So, things that depend on more than one variable. There's infinitely many examples to draw from. You could think of, the performance of a computer monitor, right, is measured in, one of the measurements is the frames per second, right? Frames per second. The lower frames per second it is, the more flickery it looks, right? The higher frames per second it looks smoother. So it's like the difference between old-timey movies and those, old, hand-rolled films versus what we have now, which, the fastest things are hundreds of frames per second. The human eye detects the movement around up to about 60, maybe up to like 100 frames per second. Then we can't tell. It looks just like a fluid stream to us. So what you could do is look at what dictates this relationship. How do you know you're going to get a certain rate or frames per second on your monitor? This depends on the power of your computer, but it can, two big determining factors you could build it around would be the memory you have available. So this could be RAM or your video memory, and then the resolution of whatever it is you're trying to display. So, we could have resolutions of like 360, 480p. You've seen these on, right, like the quality of the YouTube videos. And then the memory you have available, you might have 1 gigabyte, 2, 4, 6. So depending on what you can throw at the video you're watching, you're going to get different values for your frames per second. So you might see something like 45, 48. And you don't need to get all these down. These are really made up values. But the idea here is that we've got these inputs here of R, these inputs down here of M for memory. And so what we see in here is maybe the Z, which is the function of the resolution and the memory. Excuse me, and so one way to interpret this table, right? We pull out this 130, and how could you like interpret this to somebody who just walked into class 20 minutes late? What would you tell them that this 130 means?
It's your result if your inputs are 720 and 4 for the respective variables.
Right. 130 is the function of having 720 for a resolution and 4 for the RAM. And I just got a message in chat. Yes, these values are not accurate. So there's a few computer people in here, and you probably, I see you rolling your eyes right now. Yes, I just made these up off the cuff. My plan was to go and look up an index of like what benchmarks, but it just didn't happen. So these are made up. They are just reasonable values, but they in no way reflect reality. But this is what this would mean. Let's say we had, computers built on Planet Mali. This would be their performance index. But that's exactly right. This is what you would get, 130 FPS for this resolution memory. So what's helpful about that too, again, is when we start to talk about rates of change, now we can start talking along the different axes, right? Because a movement down a column is really a movement in the direction of increasing memory, right? And upward is decreasing memory. And then vice versa, left and right would be decreasing resolution, increasing resolution, and talking about those rates of change actually becomes pretty interesting. But for now, just kind of navigating the fact that you've got a table with 2 independent variables and 1 dependent variable. And to visualize what this would look like, the graph of, did we call this F? Yeah, of F of Rm would be the set of points. Let's back it up. R, comma, M, comma, F of Rm. So this would be a surface where your x coordinates given by resolution, y is memory, and then your z is the FPS. And so you can see it's going to be like a blanket, a surface of some kind over the xy axis that's representing the temperature or the frame rate based on your given inputs. All right. So we have that kind of numerical perspective. A couple more examples before we start diving in a little bit more. A nice equation that there's a few practice problems with this one in the text. From economics, which they call the dismal science, is the Cobb-Douglas equation. I believe that this has been maybe not replaced, but upgraded. So we're kind of working with an older model. But for a long time, it worked because it was very simple and remarkably accurate for what it did. Essentially, what it does is it defines production overall, the value of production, as a function of both labor and capital. Total labor, and total capital. So that's a multivariable function. That's two variables going in and one coming out to give a monetary quantity to all production. Okay, and so what they came up with was a function P of L, which is labor, and K, which is capital. And it's some value B times some scalar B times L to the alpha times K to the 1 minus alpha. All right, and what is alpha? Well, alpha is essentially it's not a probability, but it was like the proportion to which money was going into labor versus capital. Okay, the idea was that the exponents here equaled 1 if things were in a good ratio to each other. Okay, there are some, just like anything, you could go into a lot more analysis, right? This isn't an economics class, but if things are pristine, these two things add up to 1, which is what we have here. So we see that P is the total production. So that's the dollar value of all goods annually. L is the number of person hours. Right, so it's the number of people times the number of hours they work, so it's the amount of labor. K is total capital, which is, total monetary value for all machinery, buildings, equipment, etc. And what they did was they used 1899 as a baseline and said, all right, we're going to call this 100, right? We're going to index it and say, this was a great year to base everything else off of. And so we called this level like 100, and then everything else off of that, if it's 120, well, that's 20% more than it was in 1899. Okay, so it's a way to kind of normalize the numbers. And so what they did with that, they performed a little bit of regression from the data, and they came up with this, which is 1.01 L to the 0.75 K to the 0.25. And so I'll yoink this from the text. There was a table that they actually published with all of the year's labor and capital totals. I forgot what that value was off the top of my head. Right. So if we look at, for 1910, this was the data. We saw that the labor was 147. Again, this was indexed from the year 1899, so it's like 47% bigger, you could say, than the year 1899. And we knew the capital was 208. And so to find the value of production using this model, we'd look at P of 147, 208. So we just compute that, and we should get 161.9. And if you compared this to the actual data back then, I believe it was 159. So perfect, no, but very, very close. And again, economics is a dismal science, so they can just be pretty close and be fine. They'll just call it a day. But it works really, really well. It's very simple, and it has this 2 input, 1 output relationship. And again, a little bit of creativity allows you to see this isn't actually 2 inputs, right? There's some other places where these parameters can shift, and those things are variable as well. But if we simplify the situation to where these exponents, their sum equals 1, we're in this type of world economy, this thing did a really, really good job for a long time. So, and again, analysis can be done on there on the rates of change and such, but we're not going to get into that quite yet. So I said we'd get to the domain and range. These are things we need to understand and be comfortable with these new flavors of functions, or this new perspective on functions. So domain and range, let's maybe just start with an example. State the domain for, well, let's start with, how about this? Single variable function, what would the domain of this function be? Set of all real numbers x such that, what's the restriction on this thing?
X is larger than 0.25?
Yes. Exactly. X has got to be greater than a quarter. ln can't be non-positive values. So that's the restriction on the domain there. So if we take a look at, instead, stating the domain for this guy, z of x comma y. Sorry, this thing's bugging out. X comma y equals ln 3x minus y plus 2. Well, same thing applies, right? We know that ln can't input any non-positive values. It can't be 0 or lower. It's not defined. It has a vertical asymptote at 0. So what this tells us is that 3x minus y plus 2 has to be greater than 0. So what does that work out to be? Well, that works out to be that y is less than 3x plus 2 must be true about all the points x, y. Right? So what is the domain for a multivariable function or a 2-variable function? Well, the domain is going to be a set of pairs, right? X's and Y's, or labors and capital, right? Or memory and resolution. These pairs. So, and the pairs have to have this relationship. If they don't, then they're not in the set, right? Because then they would break the ln function. So what we have to do is define it as, all right, well, this is a set of pairs in R2 such that y is less than 3x plus 2. And so before, right, we might visualize the domain as an interval. Here's 0, here's 0.25, and we're looking at all the values in this direction would work. But down here, it's a set of pairs, which is really a region in the xy plane, right? So it's, how could we think of this? On the xy plane, 3x plus 2 is a line that we're not including. So here's y equals 3x plus 2. We're talking about all sets of pairs where y is less than that. So what's that? That's all these points here. So this is my domain D. And I'll leave you to think about the range, but just remember that the range set of all possible z values okay. So if you're looking for the domain of a multivariable function, you're going to have to go with the most restrictive set of values. Does that make sense? You have to leave out the stuff that will break any part of it. So if I have an ln and I have a square root, I got to figure out where are the values that are going to make them both happy, right? And not break one or both at the same time. Okay. So we've played a little bit with the algebra. We looked at the domain and range. Let's take a look at some graphs. I said already that, if we've got some function of two variables, the set of points x, y, f of x, y is the graph of f with, all these points x, y in the domain of f. I'll just write that out. So let's visualize the Cobb-Douglas function. And I'm going to use CalcPlot 3D. Which I don't know if I told you, this is developed by our colleague Paul Seeberger at MCC. And it's been used nationally. By a lot of schools. So it's pretty cool. This is made right in our backyard. And he's a great professor as well. So nice guy. So what we have here is a visualization of the Cobb-Douglas function. So I'm going to put it back to the home position and try to unpack what's going on here. So here's the XY plane, right? Z's upward. I'm spinning it to the right a little bit so that we can see what this thing looks like. Kind of a fanned piece of paper, right? Raised in the middle, coming back down to the axes. So, right, production's going to be minimal or nothing when one of the values is 0 and the other is too high. I'm saying this poorly. When we're all labor and no capital, we have no production, right? When we're all capital and no labor, we have no production. So on the axes themselves, production's low, but as they kind of meet in the sweet spot in the middle, the z value raises up. So that's pretty cool. And again, if you play with the exponents, this will shift the graph slightly or significantly. And then you'll also see these red lines on here. And this is where we're headed next, which are called level curves. And this is a way to get a sense of what the 3D graph is doing in 2D, right? Because not all of us are gifted artistically. And honestly, it only gets you so far. So what you can do is instead trace out what are called these level curves to get a sense of what this thing looks like. In the same way that we have 2D topographical maps, it's the same exact idea. The lines outline the different heights based on their XY coordinates. Okay. So, and there's a specific way we do this, and I'll show you how. But essentially, if you hold Z constant, what are you doing? We're saying, all right, well, at this height, tell me the set of points x, y that are sitting on this surface. Well, we can do that. At z equals 1, x and y are related in this way, and then we'll trace out a curve along that surface. And if we let z scale, it's going to keep happening. So you'll see here, z fixed at 1, 0.8, 0.6, 0.4. And so what you get a sense of just looking at this 2D map is the same sense you get from this 3D, which is, oh, as I move out in the x and the y, this thing seems to be increasing in this kind of bowed up way and not raising so much when we're out on the axes themselves. And again, you can change how much you would space these out by depending on the graph. It's not always going to be by just 0.2, right? You got to, each graph is dependent on the context you're playing in. But to get a quick sense of just what that thing looks like, and again, the link is in the lecture notes so you can play with this yourself. I find having 2 tabs of this open does not work great, so just play with the one. It's not the most optimized thing in the world. Thank you though, Paul. It is awesome. So that is what we have there. Oh, and actually one more thing I wanted to show you. Sure, Mally, we'll watch. All right, great. So there is a way to trace out along here. So this is, when you're playing with this, you can put on the trace plot over here. So this is just the XY plane, the coordinates of your point, and it will draw it out here on the surface. So if I want to know, where am I at 2, 1, it will show you where you're at 2, 1, as well as give you that value, right, or something close to that. And so this can be helpful, again, to just orient yourself, find particular values, like you're hiking along this little hill here. Okay. So it's a really neat tool. So you can use CalcPlot 3D. I'm still shocked Desmos hasn't gotten into this game. I think GeoGebra is another one that's nice. I've played with it a bit. I find it to be a bit clunky, to be honest. But another thing that scales up a little bit nicer is the idea of level curves. When I say scales, I mean up to n dimensions, because this idea actually become level surfaces. And so you can get a sense of what's going on, even when something's not 3D, maybe it's 4D or more. And then we kind of can go into equations instead of needing to graph it. So let's look at a simple example with level curves. So we've got f of xy is x squared plus y squared over 4. You might have an idea of what this looks like already. We'll find the level curves, or what are also called traces. At k equals 1, 5, 10, 20. So what we do is set z equal to k and identify or draw the curve. So for k equals 1, what we do is we set the function equal to 1. And we see, okay, well, what is this? This is really, right, an ellipse. Major axis is y, up here 1, 2. So at k equals 1, we've got an ellipse doing something like this. So again, what is this? This is representative of if we took a plane at z equals 1, right, a sheet of paper, and sent it through whatever this surface is, then it would intersect at this curve, which would be an ellipse. So then if we take k up a notch to k equals 5 and see what happens. Well, here's 5 equals x squared plus y squared over 4. And what is this? Well, it's not in standard form, but if we divided both sides by 5, get y equals, or 1 equals x squared over 5 plus y squared over 20. Right, so what's happening here? Well, this is really a ellipse with major and minor axis here. Radical 20 is what? 2 radical 5. And radical 5. So what's the square root of 5? 2 point something. That's something like here and here. And then your y values are going to be up here. So this thing's going to be pretty huge. So maybe we'll cut it in between for the next one. So what does this tell you already about this surface? Just looking at this 2D map so far. What are you thinking? We have no thoughts.
Expanding.
It's expanding. Yeah, it's getting bigger. Right? So as I get higher, it's getting wider. It has maybe this bowl-like shape. And if I changed, k to be any k value, and let's maybe cut it in the middle so that we get something relatively nice. Let's do k equals 2 here. Be kind to ourselves. Right, so this is plus and minus radical 2, so that's somewhere like here. And plus and minus 2 point something, so something like here and here. We see this will be the case. So, if I think about a point x, y here versus here, you can kind of think about how this point towards the origin is lower than this point out here, just like you would on a contour map, right? And I'll actually just nudge you to go verify this in CalcPlot 3D. And you should remember this from 12.6 too, although maybe a little fuzzy, that this is what a elliptic paraboloid, right? So it's like that parabolic bowl facing upward with elliptical cross sections going up, bowing up on the z-axis. But this is the way that we draw level traces. And this is something that is used throughout mathematics for a variety of reasons. Okay, getting level curves or level traces to get a sense of what's happening within a set. Do we have time for one more? Yeah, so let's try this. Kind of a problem. I'll say describe the surface given these level traces. Oops. Maybe I'll never get them parallel. Maybe it's a dream. These are parallel, okay? Take my word for it. Just trust me. I've done nothing to make you not trust me in this course. So let's say it's k equals 1, k equals 2, k equals 3. These are perfectly parallel lines. Can't believe how amazing that drawing is. What do you think this surface looks like, given that this is the level traces?
It looks like just a flat plane that's going up.
Yeah, a flat plane, right? If these lines were truly parallel, which I get that they're not, but if they were, then the cross sections would all be, right, these intersections would be lines with a flat plane. So the only shape that could possibly do that would be a perfectly flat plane, right? That's maybe slanted up at an angle of some kind. But yeah, your cross sections, these traces, are linear functions. And so what does that mean? That they're going to have some equation ax plus by equals k, right? Which in this case, we're replacing z with k, right? So really the function would be z equals ax plus by, and we know that this would be a plane. Does that make sense? Maybe I can quickly draw up one of these here. All right, let's try this. This is no longer, we don't need you any longer. So if A and B are 1, and this is the plane z equals ax plus by. So if I add traces in here, can we do it? Forget where that setting is. Oh, create plot. There it is. Oh, getting dizzy. So if this were the plane z equals 1x plus 1y, we can see how setting z to a fixed height would create a perfectly straight line. And if those were evenly spaced out, they'd be parallel and moving out in this kind of equally spaced fashion. If the spacing were increasing for the same change in z, what would that tell you? If the distance between contour lines here, you can see my cursor, right? If the distance between contour lines here were increasing or decreasing as this change in z were constant, what would that tell you?
Your surface has to be curved. Right?
Yeah, it's got to be curved. It's not perfectly flat, right? Because a scooch upward in the same amount has now resulted in either a larger gap or a smaller gap, right? So think about yourself walking along this hill, right? If this contour line is farther or shorter from this one, that tells you a difference in how steep you have to climb, right? If it's closer, it means you have to climb steeper. If it's further away, that means that gradient is going to be smaller. Does that make sense? The gradient will be less steep. Okay, if they're more spaced out. Cool. So yes, this would show you that you have a plane, and the change in the distances between these contour lines will tell you how fast it's shifting. Okay. Very cool. All right, and lastly, on this topic, I'll leave you with a bit of a puzzle here. Level curves for a 3-variable function. So let's say I give you a function of x, y, z, so 3-variable input, 10e to the minus 9x squared minus 4y squared minus z squared. Well, let me not write this equal to k. Set equal to k. And what do we get? So its output obviously varies on where I am in space, x, y, z, right? The domain space is in the 3 space. So it's not just the plane. I'm coming out of R3, plucking a point, and this assigns me a value. It takes, right, 10 times e to the stuff with my coordinates. So what does fixing the output value and then finding this trace or this curve, what is this going to look like? What do you think?
To give you a series of surfaces.
Yeah, it's going to give you a series of surfaces, right? So if we set, 1 equal to 10e to the 9x squared minus 4y squared minus z squared, right? What is this? Well, this is some type of surface. It's an implicit surface of 3 variables, we'd call that. We could imply that z is a function of x and y, and it would generate some surface. And we could do that with, 2 equals, 3 equals, etc. Oh, I might have to do this as an implicit surface, right? No, it's not letting me. That's not it. So we want to do a implicit surface. Say I'm actually going to let it be k equals 10e to the right? And so k I can play with. And so what we're actually getting is, all right, we hold the output constant and see what results. Well, we're getting these shells, right, instead of curves. So this is to show you that this idea scales up in dimension, right? You're not just going to get traces or curves in 2D, but there'll be n-dimensional representations where we kind of remove a variable to think about how this thing would look or how it plays. So here we'd get shells or trace surfaces. We call them level surfaces. Let's shift back here.
So does that mean that, you know, if all of these things can vary freely, that this function will fill all of 3 space, but they have to maintain specific relationships to one another, so it can't fill, like, some parts of 3 space are, it's connected, right? So if it fills one part at some time, it has to fill exactly, you know, that ellipsoid or whatever.
So it will solve. So depends on what you're asking, but yes, you know, since this thing has no domain issues, right? It is a chain of 2 continuous functions, right? E is a continuous function. This is just a power function or a polynomial rather. It will fill the entire space. Now again, if the point solves, if you have a 4-coordinate point that solves this equation, right, where here's your output and here's your 3 inputs, then it will lie on one of these surfaces. And I think that's what you're talking about. So if you have a point, it will live on one of these. But again, that would be living in the 4 space, not the 3 space.
Okay, I was just going to ask if we were in 4 space at this point.
Yeah. Coordinates, you know, again, it depends on what our interest is, what our point is. Here we're stretching the value of this exercise, which I'm totally cool with. But yeah, you would be if you're talking about the graph of this thing, it would be the coordinates x, y, z, and then, you know, f of those 3 things. And we can't really visualize it too well, but we can use these as guides to kind of glimpse the upper dimensional. Yeah. All right, cool. So that's a little bit of what you can do. And again, what I wanted to point out here is one way that you can do this without really the graph is you can think about, all right, how could I visualize having an output, let's call it t, where my input is 3 coordinates? Well, you could really think about, you know, where I am in space. So let's say I'm out here. It's really the temperature at that point in space, right? You give me the coordinates of where I'm at, and then that 4th dimension is like a felt dimension, right? How hot is it? Or how loud is it? Something like that, right? Or how long did it take me to get there, you could think, as like a 4th dimension. So whether it's, you know, hot or cold or whatever, that would be like your 4th coordinate. So it's, again, a way to kind of hack your intuition for that next dimension up. So your 3 coordinates give you where you are, and then that 4th might be, again, sound or sense, like temperature, something like that. So it's like a 3D input to a 1 output. All right. So what have we done so far? We've looked at the idea of multivariable inputs to single variable output. We looked at it from a algebraic perspective, how we plug in and get values, graphical, the different variations on how these graphs could look, how to intuit it out a little bit, how to play with the tables. And then also the big idea was really level curves and level traces. So again, your sketches of these don't have to be perfect, but they do need to make some sense to you because that's what they're supposed to do, is kind of be a guide. So what we're going to play with for the remainder of this is set the foundations for doing calculus with these types of functions. And what do you remember was the underpinning of calculus from Calc 1 and Calc 2? What should we call the underpinning of calculus? Say again?
Derivatives.
Derivatives were definitely like the main idea in Calc 1, right? But what undergirds derivatives? What allowed us to take the instantaneous rate of change instead of just, goofing around with this average rate of change thing all the time?
Looking at limits.
Yeah, limits were the silver bullet, right? They were the thing that allowed us to get past the problem of dividing by 0 by just not doing it, right? By just approaching it instead of actually dividing by 0. So yeah, limits were the key. And so we're going to look at it here. Albeit briefly, but I do want to discuss some conceptual stuff and work a couple examples. Again, for the math majors, I'm going to insist that you walk through one of the purely theoretical proofs in the text, which is on page 944. You get the formal definition. Page 947 for the math majors. And I don't say that to be exclusionary. If you're curious and you're not a math major, go check it out. It's fun. It's cool. I say that because people who are going on to the more theoretical stuff are going to want to play with this before they move on to set theory and logic and topology and things like that. This is a nice playground for that. So we call these delta epsilon proofs. And it's a way to prove that a limit exists using a proof structure that's aligned with the definition. And you use it a lot in analysis, and so it's a good thing to go check out. But since that's rather difficult and bears very little practical use, we're not going to focus on it here too much. And especially because limits now are a little bit more complicated. So what was the idea of the limit before? Right, it was that it equals some number L if what? The limit from the right was L and the limit from the left was L. Right, from a graphical perspective, if I had some function, some value a, and some limit L, we said that as we come in on a from this side and from this side, as long as you're still approaching L from this side and this side as we get closer and closer, we're going to say that limit exists. And that was an if and only if, right? Both one-sided limits had to equal the same value. And we said, as a side note, what was the idea of continuity? What would we say? Something's continuous. A function's continuous at this point if
it doesn't break at all. Like it goes from like negative, positive forever, and there's no like break in it at all.
Yeah, there's no break, right? You don't have to pick up your pencil, is one way I've heard it described. There's no jumps. It's a continuous curve. And formally, there's a way we can describe that using limits. It's very much just a rigorous way of saying what you just said, Nate, which is there's no breaks. The function is approaching that point, and the last stipulation is that it actually goes there, right? So it's continuous at x equals a if the limit of f of x exists and it's equal to f of a. So it's approaching that point and it goes there. And then we say it's continuous on an interval if it does that for every single point, which is not a lot to ask of most of the functions we care about, right? They're all continuous for the most part, except for those weird ones. Hyperbola, log functions, etc. Things that have domain issues, square root function. So what made this easier was that it was in 2D, okay? This notion of approaching the point from both sides was key, and what made it really easy was that we just had to do it on a number line, right? Because what was the domain of this function? Well, the domain was the number line, right? All the possible input values for x. What's the domain for z of xy? If we got a 2-variable input.
Ordered pairs.
Yeah, it's ordered pairs. That's no longer a number line that we're approaching in on. It's a plane, right? It's a region. So domain or whatever disk or neighborhood we're around and we're approaching some point, we want to talk about, does the limit exist? Now we're talking about approaching a point, and there's not just one way to come in. And it's not even that just there's two ways to come in. There's infinitely many ways to approach a point within a region, right? You can come in this way, come in all fancy-like with a squiggle, right? We can come in on some curves. So that really changes the game. So let's write that down. Now for, z equals f of xy, we'd say the limit of f of xy, the limit of z, as these points get closer and closer to AB, this equals L only if this happens along all pathways. And again, that's why the formal definition kind of covers our butt here, but I'm going to put like in quotes, only if on all paths to AB for all xy. So what I mean by that, because this is kind of hard to wrap your head around at first. But here's the idea. If you ever driven up to like the Erie Canal, okay? You've got a stretch of road that ends, and then the canal is here, right? And then over here, the road continues. Maybe a bridge drops over it at some point, but what can happen graphically is that you will be approaching along this trajectory, and for all intents and purposes, it looks like you're approaching this height, right? This z value of, let's say we're 6 feet from sea level. But if we were on the canal, we know that's got to be lower than that value, and we see actually, as we get closer and closer to this point, this is a height of 3 feet. So I get that there's a big gap there and it's not, really getting infinitely close. But this is the idea that can happen with a surface. These things can have places where they punch out, and depending on the trajectory you're coming in on, it looks like it's heading to one value, but on a different curve or a different pathway in with the points on the XY plane, it's actually heading to a different value. And so that's a different level of complexity, and it's something that we have to look out for. And it's kind of the main focus that you're going to be in terms of practice problems. If something's, if you have a limit problem and it's not just a continuous function, or there might be some issue, that's what you're going to be looking out for. Is it on different paths that I take in? Is it actually heading somewhere different on those two paths? And that's how you show that it doesn't exist, and it's pointing back to this initial concept, which is that it has to agree from all directions into the point. That's how we know that the limit exists. Okay, so with that being said, let's take a look at a couple examples. Oh, I got a question here in the chat. Is the directionality of limits going to change once we're adding more dimensions? I.e., now we also have to go up and down. Yeah, so at a certain point, I mean, we're not going to do too much formal limit work in higher dimensional stuff, but that does track. And it's, again, this is why you move to the epsilon delta proofs, because it proves it completely theoretically and in the general case, instead of having to conjure up counterexamples or try to patchwork something together. So hopefully that covers that. I realize it's just an orientation shift from being left right, but yes, there's an up down, and yes, and then again, once you go to R4 and onward, that changes, right? And you can no longer use the analog of the Erie Canal. That's for sure. So, all right, let's pivot over here to some limit examples before we go. All right. One nice thing to know, composition of continuous functions are continuous. That's really nice, because what do we know about continuous functions? It's continuous if the limit exists and it's defined there. So mechanically, when evaluating a limit, if we know a function's continuous, then the limit is just what the function's value is at that point. We don't have to get too crazy. Obviously, the more interesting problems are ones where maybe the function's undefined or there's some sort of issue with the approach. But in general, if you have a composition of continuous functions or you have a continuous function, you know that the limit will exist and it's just equal to that value. So I'll say examples with limits. Compute the limit as xyz approaches 2, 1, negative 1 of the function 3x squared z plus yx cos pi x minus pi z. All right, so this is a 3 variable input, 1 variable output. And so we see here that this function is continuous at this point in question, right? At 2, 1, negative 1, this guy has no problems. This guy has no problems. So since it's continuous at this point, we can just simply plug in the values and move along with our lives. So this is really 3 times 2 squared times negative 1 plus 1 negative, plus 1 times 2. Which ends up being what? 12 plus 2 cosine of 3 pi. Should that be negative? It should be negative 12. Cos of 3 pi is what? Negative 1? Negative 2. Well, this is negative 1. So this is minus 2, so it becomes negative 14. Okay, so if it's continuous at the point, you can just plug in and evaluate it. So here is an example where we need a little more consideration. So let's say we're taking the limit as xy approaches the point 1, 1 of this 2x squared minus xy minus y squared all over x squared minus y squared. So what's the maybe obvious problem here?
You're dividing by 0.
Dividing by 0, not allowed. From what I'm told, can't do it. So what do? Well, we're not stuck in our tracks quite yet. Use all the tools that you have. Use all the algebra at your disposal. It's a rational function. So the ideal situation would be that this is removable discontinuity, right? So hopefully I can factor this thing and make it happen. So let's give that a shot. So if I try factoring the top, luckily these things don't look too terribly. So this would be the limit of 2x plus y, x minus y, all over x plus y, x minus y. And so fear not, that is a removable discontinuity, right? That's just a hole. And so that becomes the limit 2x plus y over x plus y. And these two functions are continuous at this point, right? This f over g. So we're good to go. This is 3 over 2. So if you have a apparent discontinuity, give it a shot with some stuff that you know, possibly even L'Hopital's rule, to make it happen. So the next are going to highlight a little bit more of the issues that are unique to 3D calculus. All right, so let's take a look at this one. And there will be a few of this flavor in the practice problems.
Unique specifically to three-dimensional examples, or unique to higher than 2?
Higher than 2, thanks. So something like this. Okay. So what we'll see here is that it's not continuous at the point. Is it? No, it's 0. So it'd be 0 at this point. No, it would be undefined. It'd be 0 over 0. So, but that's not really the point, right? We're asking if this limit exists. So it doesn't have to be defined there. We're curious, is it pointing at a certain value from all directions? And so one way that you can attack this is by showing that depending on the way I approach roadside versus canal side, right, that I'm actually approaching a different value. So we got to think about our path of attack. Okay, so what we want to do is first approach, if it makes sense, this is a good way to go, along the x-axis. Why would we do that? Because along the x-axis, all your y values are 0, right? So it's a good way to kind of simplify the problem and take a look and see what's happening as we get closer and closer to the origin. So we'd say this limit, and if it exists, right, this limit's going to equal that limit that we come up with. So we'd take a look at f of x, y. We're going to look at the limit of x comma 0 approaching 0, 0 of x squared, 0 squared over x to the 4th plus 3, 0 to the 4th, which is 0 over x to the 4th, which is just 0. So it would appear as we're coming in on the x-axis here, that the height is approaching 0. And this is really, coming in from both directions on the x-axis. So now we can come in on the other axis, and again, we'll hopefully get the same simplification. I'm just going to jot this down as coming along on 0y to 0, 0 of 0 squared y squared all over 0 to the 4th plus 3y to the 4th, which is 0 over 3y to the 4th, and this is equal to 0. And so we see some somewhat compelling evidence that this limit might be 0, right? As I come in on the y-axis, it looks like it's heading to that point. But I don't want you to get confused by this because this is not the only way to get there, right? We could come in from infinitely many paths, and we might just be coming in at the road side and not the canal side, right? So there might be some fold in the surface that we haven't found. And so specifically, if we come along on a curve, so I'll say, don't get fooled. Try another path. You could try y equals x. Okay, what is that path? Well, that's like coming in on this line, right, and approaching in here and seeing what is it, what is the surface, what is the height going to. And you could try this for any slope line, right? It's a good way to kind of get a lot of different perspectives on this curve. Where is it heading? But we'll try y equals x to keep it simple for now. And so how this will look then is the limit as x comma x approaches 0, 0, because we're letting y equals x. So this is going to be of x squared over x to the 4th plus 3x to the 4th. So that's x to the 4th over what, 4x to the 4th? which ends up being a quarter. So what does that mean? That means that, well, if we come on the coordinate axes, it looks like it's pointing at 0, that the height is heading towards 0. But if we came in on the line y equals x, it's actually a little bit higher than that. So does the limit exist?
No.
No. And so I'll say over here, you could try y equals mx to be more general too. And just leave m as a constant and see if anything pops up as an issue. So this is a way to disprove that a limit exists. All right. So I wanted to show you, again, kind of what that would look like. I know I gave you the idea of the canal, but that only has so much mileage on it. Let's see, this is squared y squared let's take a look. All right, so this is this thing, this beast. Maybe I can change how many grid lines I have, up the fidelity of this thing. So you can see as I was going along the coordinate axes, right, it looked like it was heading to 0. And obviously these boxes are kind of pixelating the image, so really it gets a lot closer in there. But along the x and y axis, it looks like it's heading to 0, but really along y equals x and y equals negative x, it's sitting higher, right? So this is a problem that's unique to the higher dimensions that wasn't an issue we needed to consider in R2 because we were just moving along a number line. That was our only option, right? Now we're moving along the xy plane and seeing what could possibly happen. So there are some fun, kind of things that can pop up with that, and I'll leave you to play with them in the practice problems. Let me make sure I didn't have anything else for you guys. So when working on limit problems, try if they're continuous, you know that the limit will exist there. If not, you can try this plan of attack to see if you can find a hole. You could try graphing it to maybe help generate some points where you can disprove it. Otherwise, use what tools you have available. Again, L'Hopital's rule, whatever. And I think that is it for that unit. Are there any questions right now? All right, cool. So next time, again, we're going to start looking at, now that we can talk about limits and moving points, moving along a region, right? How is the surface changing with respect to the direction that I'm moving? And eventually, right, we're going to start with going along the y direction, the x direction, right? And like I said before, like along the memory direction or the resolution direction. And then if we have n variables, how do we measure, moving in that direction, or a mix of all of them, right? When I'm moving in this direction as a vector, how is my height changing, right? Instead of just with respect to the different coordinate axes. So that's pretty cool stuff. You can do a lot of interesting, optimization problems using that tool with multivariate. So that's the exciting stuff we're headed towards. But I will respect your time and cut it there. If you got questions, please hang out. Otherwise, have an awesome weekend, and we'll see you next time. Bye now.
I have one question real quick.
Yes, sir.
In terms of the relationship